my major focus is in explainable planning and decision-making algorithms. And what I'm going to talk about today is what do you do when the plans that you are generating are not what the end users are expecting. So how to deal with the end user expectations, how to explain when those expectations do not match, and a bit about the dual use of technologies in that space. So you can use the same algorithms to explain as well as deceive, for example. So I will touch a bit on that towards the end. So let's consider the very simple setup of any human AI interaction, right? So there's an agent with a model of decision making. So this could be, so the model could be like a planning problem, a decision theoretic problem, a graph, anything, right? So, but it's a model of decision making. And usually, when you are dealing with end users or humans in the loop or just observers, they usually come with expectations of your capabilities. And so that would be a mental model of what you can and cannot do. And that's true not just for robotics, but for, in general, softwares and any kind of agent. And the real problem arises when these two models do not align. So the human expects things that you can do that you actually cannot, or vice versa. And so in those cases, you'll be stuck with scenarios where you, even if you're doing the best possible plans you can, your plans would be evaluated by a mental model that's different to yours. And so they would come up to be inexplicable or unexpected. And so as an agent in these scenarios, you have sort of two options. So if you want to have good collaboration, you can either make explicable plans. So these are plans that are expected from the user's point of view, given your understanding of what the mental model is. Or the other option you have is to do the best you can and then explain why you did what you did in terms of those model differences. And these are usually sort of two sides of the same coin. So the explanations are in the space of models. So you're explaining to the end user in terms of artifacts in your model, whereas the explicable plans are in the space of behaviors, right? So you're changing your behavior, possibly doing a suboptimal behavior, just to ensure that you do not have to explain later. So before going into sort of a little more detail about this, I would highlight a few examples where these model differences do occur. So the first one is in terms of a smart room environment. So this is a smart room at IBM that I worked on for a while. Here, the robot you can think of as the entire room, right? It's an instrumented room. There are a bunch of speakers, cameras, listening and processing what it's seeing. And as the users in the room, you really have no idea what it's hearing and what it's seeing because it's distributed. And so as you work more, the understanding of what the situation is in the room kind of diverges. Right? You have a set of facts and you don't know what set of facts the system has access to. And so the decisions that you come up with often require a sort of retrospection. You could think of model differences in terms of intelligent tutoring systems, for example. So here the student model is the user model, and it's an incorrect and incomplete model. And the systems model is the instructor model. And the job of the system is really to get the student model to a point where they're able to correctly answer questions. So to get it as close as possible to the instructor model over time. You can also see these model differences in terms of decision support systems where the humans are the actual planners. So for example, when NASA says planners, they usually talk about human planners who are making crew schedules. And in those cases, the planner's job is really to help the human make better plans. And there again, you have difference in capabilities, information that the system has access to versus the humans. And you have to navigate these differences in order to come up with plans that the system and the humans mutually agree with. Um, in a sort of a different sort of setting where there are humans providing models as well. So these are systems like dialogue systems where there are people writing down complex dialogue trees. And after a point of complexity, there's very little control that the humans have over the final output. And so there's a divergence in the actual model they write versus the model that they think that the system has. And there again, you have to model these differences. And so in each of these cases, sometimes there are humans writing models, sometimes you are the end user, sometimes you're the one making plans. And there's always these differences in models between the end user and the actual system. And in all of these cases, these are planning systems, but you could think of softwares in general where these differences happen. One example where I will go into a little more detail is in search and rescue scenes, where there are robots that are internal to a disaster response scenario. And there are external humans or commanders that are providing it high-level goals. Here you find differences in models because you start with the starting blueprint of the building, for example. And then once the robot is in the scene, the robot's understanding of the scene has changed, and the externals do not have access to all the changes that has happened, right? So you can think of a robot that has sensing capabilities and is updating its understanding of the model, and the external only has a partial view into what the robot sees. So if you consider this scenario, the differences in models would be in terms of roads that have opened up, or maybe there are rubble in places where there were paths before. And so you end up with plans that are either not executable in the externals model, or they are severely suboptimal. And so the external would be wondering why you're coming up with circuitous plans where you didn't need to. And so just to motivate that a bit, let's look at a quick demo. So here, so this is the externals point of view on the top right. And what the robot is communicating here is the plan. And that plan includes the rubble removal action, which is, of course, costly to the robot, but it's just so that it's closer to what the expected plan would be. So that's the explicable part of it. Whereas if you, in the second example on the top left, the robot is giving updates of the model to the user. And with those updates, the resulting plan is actually optimal in the revised model. So that's the trade-off that we are trying to get to in terms of should we lose optimality and conform to expectations versus explain and then stick to the best plan in our models. And very briefly, how you achieve this is what we call through model space reasoning. I won't go into the details of this, but just to highlight two concepts in it of completeness and monotonicity. What completeness tells you is that the point of an explanation is to really negate foils that the humans have come with. So foils would be why not this plan, where the other plan is the foil that the human thinks you could have done. Or you could ask why this plan, where the foil is all other, as opposed to all other plans, right? So the foils are things that the explainee thinks that are better options in your model. And so what completeness gives you is a guarantee that all foils, implicit or explicit, have been negated. And monotonicity is a property of explanations on top of that, that guarantees that no matter what you explain later, as long as the agent's model doesn't change, the previous explanations would always be valid. So, and of course, minimality in both those cases means it's the shortest explanation that can give you those properties. And the fact that these two exist and are different would lead to some interesting properties which we explore later. But the thing to keep in mind is that we are trying to minimize the amount of information in the explanations to ensure that we are not giving irrelevant information, but we want to be complete in the sense of negating possible foils. And optionally, we want to be monotonic as well. So later on with further explanations, we do not negate previous explanations. And we'll come back to this a bit in later. So that's briefly the overall goal of dealing with mental models, right? So we have an option in the space of behaviors to conform, or we have an option in the space of models to explain. And recently we have been exploring what happens if we bring in the option of model space reasoning in the plan generation process itself, right? So what if an agent could consider the possibility that it has to explain later and change its behavior at the time of synthesis of those plans? And as humans, we do this all the time, right? So if we know that we have to explain our behaviors later, or just that we are observed, our behaviors change. And what we wanted to explore was, what does that mean for an automated agent? Specifically, the two costs that the automated agent incurs in dealing with mental models is, one, the cost of explanation, and two, the cost of suboptimality in order to conform. And so you could think of this trade-off in terms of those two costs, right? So you can fold in the cost of explanation later and the cost of departure from optimality in order to conform in the planning process. And what you end up with are algorithms that can actually think of the implications in terms of interaction at the plan generation time and not later after the plan has been generated. And from the computational point of view, we were actually showed early this year that it's no harder than the traditional planning approach. So you do not actually lose a lot in terms of computation, but you actually gain a lot in terms of the interaction that will happen later by considering the impact at plan generation time. And so this really changes the paradigm of how we think about planning, right? So the original, the classical way to think about planning is you're given a model to plan in and you produce a plan. So this could be, and this doesn't have to be like the classical planning approach. It could be an MDP where you produce a policy, or it could be a graph where you are just computing shortest paths. And then the point of explainability in human-aware planning is, given the model of the problem and given your approximation of where the human model is, you're really trying to find out what's the right model to plan in. And so the solution is no longer just a plan, but also a directive on how to interface with the human in terms of that plan. And that interfacing for the purposes of what we talked about so far is in terms of explanations. But this is really a general way of looking at the different forms of interfacing that can happen given a plan. And we call this the different forms of interpretability. Explicability is just one of them. But in general, you can talk about, so there are other forms of interpretability, like legibility, where you're trying to predict the model of the agent given observations, or predictability, where you're trying to predict the behavior given a partial observations. So in all of those, you have the option to think about how to actually interface on those policies later at plan generation time. So for explicability, the other side of the coin is explanations. For other forms of interpretability is communication in terms of the internal models of those agents. And so, so this trade-off is kind of more general than just these two instances. What I would like to highlight a bit in the second half of the talk is that this is also dual use, right? So if you have a mental model where you can enhance the interpretability of a plan, you can also use that to decrease the interpretability of the plan. So these would be deceptive algorithms. And so there's a lot of work on actually showing that you can use the same algorithms that you use for interpretability in order to simulate behavior that's kind of obfuscating your actual intentions. In this talk, I will just touch upon one of those cases, of false explanations or lies. And the idea here is that we are going to use the same process of model space search that we talked about, and try to tweak that a bit to generate plans, to generate explanations that are not true, but also conform to all the specifications of what an explanation should be. So if you think back on the model space search scenario, you have the users, you have an approximation of the user's model, and you have the model, you have the ability to produce minimal explanations, which are either complete or complete and monotonic. And so if you just look at an example of what that would look like, so here again, the agent has come up with a very circuitous plan, and this is the plan in the external human's mental model. And so the human would be thinking, why this one, right? So the reason is because the model has changed, and the robot is trying to navigate those changes. In the minimally complete case, you can just communicate 2 of those 5 changes, and now it becomes clear why that plan is the way it is. For an explicable plan, you can have a much more costlier plan that includes removal of rubble in order for you to not explain. But if you think about this space of models, so in the middle, I have put 2 dots there. That's the region where you can actually think about using these same algorithms to provide explanations that are not part of these model differences. So in the previous case, you were confined to these differences in this and the space of these differences. What you can do is to come up with what we call the lies of omission and commission, where you are trying to get out of these space of model differences and come up with explanations that are not true, but do have the completeness property. The first one is a bit of an abuse of the term omission, because you're still committing to facts that are not true. But the general idea is you're removing parts of your model and still justifying your decision. So you may not actually have, you're not guaranteed to have this form of a lie. So if you're looking deeper into in the framework of model reconciliation, the places where you can actually generate this is when you have a mental model where the mental model lies somewhere between the minimally complete and minimally monotonic explanations of an empty model. So only under those circumstances, you can actually remove stuff from your own model in order to justify with your behavior with a false explanation. So what that would look like in practice is a robot saying they cannot do stuff they can actually do. And that would satisfy all the properties of an explanation, even though that's not true. In the second part, in the lies of commission, you're actually going out of the space of models. So here you would be saying things like you can do stuff that you actually cannot do. So it's the inverse of the first case. And there also, you satisfy all the completeness properties of explanations. And there are actually algorithms that can do that, right? So there are open world algorithms that can extend models with new facts. And you can use those model extension techniques to generate models outside the space of model differences. And so, so what that would look like in this example is that given these differences, this is just a single change in the domain, and you're able to justify your plan. And notice this is smaller than the previous minimally complete explanation. So that requires 2 facts. This is a type of commission, lie of commission example, where you added stuff to your model. So there's a rubble where there wasn't any. And you're still able to explain it with 1 single fact change. And of course, if you're talking to a planning person, you can always say there's a wampus there, and we will always believe it. So the real question is, do we actually need the ground truth in the explanation process, and to what extent? And in general, explanation is a subset of things that you can do to persuade the end user that what you did was the right thing to do. And this is not really surprising, but the key takeaway is here that it's not really a fear-mongering kind of sense that we can lie with algorithms. There are algorithms that can already do it. And we have, in terms of the technical details, you can look at the papers and the links to see how exactly to run those algorithms. The real question is when and how, right? So there are advantages to be had out of this. So sometimes they are computationally easier. Sometimes they actually may increase the efficiency of an interaction. So if you think of equivalent in human-human interactions, like we never learn let's say we never learn laws of relativity before we learn Newtonian physics. So at that point, the simpler explanation, which has a lot of omitted facts, are actually the truth. And so even in the case of human AI interaction as well, when the model of systems gets too complicated, you can get by providing explanations that are not true. That actually helps interaction. So there are a lot of things to consider there, whether how much of that is really a thing that we should do, given it impacts the mental model going forward. So interactions are not, it's not episodic, they're long-term, and they do affect human behavior later down the line. In sort of a precedent to these sort of behaviors, one example that we studied a lot was the doctor-patient relationship, where the use of deception for this kind of a greater good argument has been argued for a long time. And I mean, sure, the prevalence of this has decreased over the years, but it's still not completely unheard of for doctors to withhold information for the recovery life cycle of a patient. Right? So a couple of points just to that we can take away from doctor-patient relationships versus what we do in human AI collaborations is that it all boils down to consent, right? So you cannot model the entire world. There are a lot of uncertainties, and things will go wrong at some point. And so if you look at the case law and look at what has happened in those cases for doctors and patients in particular, it always goes in the favor of the patient when things go wrong. And in particularly, even in the second case, the interesting part was that even if when the defense testified that they would have not changed their decision when they were given the actual facts of their illness and recovery plan, even if they knew that, they would not have changed the decision. Even then, the doctor was guilty, and that's because they did not take the required consent from the end user. So what that means for us is that if we are actually putting these algorithms in place to justify some sort of a greater good argument, then there has to be user agreements going into that. And that kind of has a domino effect, because once you have the user agreement, when the user understands that the agent might make up stuff sometimes, then it also affects your trust going forward. And you can see some of those effects in how placebo medicine has been treated over the years, how perceptions and attitudes towards it and its usefulness have changed over time. And finally, it's also the case that the doctor-patient relationship is not so symmetric as certain human AI collaboration cases are, at least from the point of view of the AI. It's not certainly not in the same seat as a doctor right now, but we would get to a point where at a certain stage that AI will have much higher computational and data bandwidth than we have. And so at that point, there would be this asymmetry in capabilities, and there would be much more parallels with that sort of a setup, right? So it's a good basis. The doctor-patient understanding is a good basis for studying many of these cases. So I would stop here. And as key takeaways, just mention that that mental modeling really offers a broad, powerful set of capabilities. If you're designing cooperative agents, you have the ability to conform to expectations and explain your behavior and do both at the time of plan generation, but it's a dual-edged sword, right? So you can use that to mislead and deceive, and the algorithms to do that are already out there, so it's not hypothetical. The question is to understand when that's something that it should be considered, if at all, and the ethical and legal ramifications of it. Especially, we can look at similar parallels in human-human interaction and understand and kind of translate some of that into how we design human AI collaboration as well. I will stop here and happy to take questions.
Great, thank you very much for your talk. It was very, very interesting to me to think about this possibility of robots deceiving when asked for explanations for their plans. So the floor is open for questions. Anyone is free to write a question in the chat box, and we will either read it out loud, or you can just say that that you have a question, and we'll pass the mic to you. Meanwhile, I would like to ask a question. Mm-hmm. So this going to this matter of deception, I think this is a very interesting issue. I understand there's also benefits of doing that for the sake of the team dynamics. Mm-hmm. But then when I think about, for example, this being part of, for example, a black box of a robot. So as part of an investigation, to connect this to Alan's talk earlier today, mm-hmm. you can have a black box that allows you to ask questions. Why did the robot do this at this time, in order to investigate the action, and this thing could lie. So mm-hmm. how can we guarantee that, for example, a planning, an explanation method will not lie, or how can we detect that the method is lying, either technically or institutionally? I don't know. Any thoughts?
Yeah, well, we have actually thought a lot about that question, and we don't have good answers. So it's mostly on the developer side. Like whoever is making the algorithm has, if you are specifying what it can or cannot do, then you can make sure that it doesn't happen. So there you can put constraints, like any information that comes out of it is consistent with its ground truth, like its understanding of the ground truth. But if it's from the user's point of view, there's no real way to tell whether that's true or not. From a single interaction, the only way you can try to estimate a possibility of where things might have been wrong is in future interactions, where you can assign it tasks and see if it can do them or not. So for example, like a strawman example, if the robot says I can fly, and then you ask it to do something that requires flying and it cannot, then you can have a sense that probably it was not true. You wouldn't know for sure, because it could have chosen something. It could have still done the task without flying, and you don't know if it didn't do it because it can't, or it didn't do it because of some other reason. But based on longer term interactions, you can have like a sense of where the actual model is. But from a single interaction, there's no real way to tell.
Great, yeah, thank you for the answer. So I'll ask another one. So you've showed some examples, practical examples in robot search and rescue. Mm-hmm. And I'm trying to think of other use cases in robotics, but in use cases that are used today. So I can think of robots being used today in agriculture, mm-hmm. or inspection or maintenance or offices. But when I think, for example, of an office, I don't really imagine myself asking the robot, why are you taking me through this corridor?
Yep.
So my question is more like, is explainability a tool for developers to use in debugging? Or is it, or could you tell us of some specific use cases that you've thought about, where lay users also need explanations?
Right. So I think so the examples that I showed you, some of them are deployed algorithms, and one of the most fun examples was the smart room example, because It's really a distributed, like embodied agent, and one of the so this is a real thing that happened. So we were making the system more and more proactive in the sense that it could take more autonomous decisions, and we were actually demonstrating this one day to a client, and the system kind of interjected and said, should I do this? Now, from the design point of view, we wanted the system to do that because we wanted it to be more proactive. But what actually happened was that the users in the room were freaked out. Like, how does it know that it has to do that? And why is it saying it? So one of the things, so that the intent really didn't match out the actual interaction in the end. And the reason for that is our understanding of where the room was, like the state of the room, was different from where it actually is, because we do not know what it sees and what it hears, and we do not know the higher order, the reasoning layers above what the sensory inputs are. So what we did was we added a capability where we could always ask, so what do you see right now? What do you hear right now? What are you getting out of those individual um, uh, inputs? And then how are you deciding? So progressively higher and higher order uh, reasoning capabilities, what we could go into those and make sure that it's on the same page as we are. So that's one of the deployed applications where these differences in mental models really played out a lot. And in the sort of the solution was always to make it more transparent, right? What's going on inside, starting from the sensory inputs to progressively higher order reasoning engines up to the planning and reasoning as well.